This problem further explores buoyancy, similar to the way that the stand-up paddleboard question did, in that we have to account for some other mass that exists in the problem, right? Our first buoyancy problems were a balance between the buoyant force and some mass of an object. And here what we have to realize is that there's some buoyant force. We're working with this. And here we're doing this problem with this blimp up in the air. And we have to realize that there's some buoyant force from the blimp displacing some of the air. But the thing that it's displacing the air with, which in this case is helium, also has some mass. So we have to think about how that factors into a buoyancy calculation. So here we have our blimp. I drew a blimp. And as always, the first thing to do is to draw a free body diagram describing the forces, right? So there's some buoyant force from this whole volume displacing a bunch of air, right? This volume has displaced a bunch of air, so there's a buoyant force associated with that, right? So that's the first thing we have, is this buoyant force. What are the forces other forces are acting? Well, there's the force that's just from the mass of the balloon itself, m balloon times g. But there's one other thing that we often don't account for, and that's the fact that this balloon is filled with a gas, and that gas has a mass, right? And so the other thing we have to account for is that there's some force that is the mass of the helium times g. Okay, so let's write down what all of these forces are. So FB, the buoyant force, is equal to the density of air, because that's the fluid that's being displaced, times the whole volume of the balloon times g. Okay. The force of gravity from the balloon itself, the mass of the balloon itself, is simply the mass of the balloon times g. And then there's some force from the mass of the helium. And that's equal to the density of helium, right? It's equal to the mass of helium times g, but we know we can write that in terms of the density of helium, which we're given in the problem, times the volume of the balloon, the total volume of the balloon, because it's filled complete with helium, times g, right? And so it's clear that one thing to be careful of is that these volumes are the same, right? The helium is displacing all of the air to make the buoyant force. So in equilibrium, so we write down our force balance here. In equilibrium, we know that the buoyant force that's acting up minus F balloon minus F helium is equal to 0, right? The net force on an object is equal to 0. And so this lets us get this equation, which is rho air, which is the buoyancy force times the volume. One thing to note is that g appears in every term, so it cancels out. So I'm not going to write down the g. Minus the density of helium times v minus the mass of the balloon times g is equal to 0. And what we're trying to do is we're trying to solve for the volume of the balloon, right? That's the main thing that we're trying to solve for. So I'm just gonna factor this out. I recognize that I can pull out a v times rho air minus rho helium. That's a nice little expression, right? We see that maybe the buoyancy force has to do with the difference in densities, right? And it's just equal to the mass of the balloon. And I said I was going to cancel the g's, and then I didn't, so I got to make sure to correct that above. Okay. And just doing one more step here, we get v is equal to the mass of the balloon divided by rho air over rho helium. Okay. And yeah, we're ready to plug in some numbers. We can the mass of the balloon is 80 kilograms, we're told. And the densities of helium and air are 1.28 minus 0.179. And the units of both of those are kilograms per meter cubed. And so we get 72.7 meters cubed as the size of our balloon, right? And I guess the thing to look back on is if the balloon wasn't filled with helium, we could just set this to 0, and we'd get our equation m balloon over rho air. And this is the kind of equation we would normally get if we weren't accounting for the mass of the helium. So, everything makes sense if we set the mass of the helium to 0.